session for the ISGC, and it's a truly Italian session. That's why I said buongiorno. Of course, we'll still keep to English. Also, I have Italian ancestors. My Italian is restricted to ordering pizzas. My name is Dieter Kanzlermüller. I'm the chairman now, and I have a wonderful co-chair, Kento Aida, who will also help and check out the chat and see if we get your questions. So if you have questions, feel free to put them into the chat. We start with the first talk by Professor Daniele Bonacorsi. He's an ordinarius, so as we say, a full professor at the Institute of Physics and Astronomy at the University of Bologna. And just thinking of Bologna, it must be lovely there now in spring. Probably beautiful weather, and first of all, beautiful food, of course. Unfortunately, we have to be here. So our excitement now is to listen to a talk of Daniele. And I'm handing over, Daniele. The floor is yours, and we're looking forward to what you have to tell us.
Okay, thank you very much. Can you hear me okay?
Wonderful.
Good. So thanks for having me today. Yes, the weather is amazing outside here. Unfortunately, we cannot move much as anybody else. And the restaurants are mostly closed apart from takeaway. So it's a bit sad. It's a pleasure anyway to be with you at ISGC, at least virtually and not in Taipei. So let's hope the best for the Bologna side and the Taipei side for next year, at least. So today we speak a second about machine learning in high energy physics. And just to set the scene, I think that the goal of this talk is trying to give a feeling of how machine learning sort of exploded in the high energy physics sector, and which might be the following evolutions of this story. First of all, we need to set a bit the scene. The scientific computing definitely has been enabling the high energy physics program, and software and computing have not been a limiting factor for physics discovery, as we know, by the way. But this needs to remain true. And to do this, we need to face some challenges that are clearly ahead of us. There are some usual ones, in the sense that computing remains a significant cost driver in our activities. Of course, the computing models continue to undergo some evolutions, more or less adiabatic, but this continues over the years. But there are new challenges, a global ramp up, let's say, in the resource needs in the next decades, coming from existing coming into the scene. And so we need to optimize further, to go deeper, to evaluate new technologies, to adopt some of these, and so on. There is an additional some complexity coming from the uncertainties in the quantitative definition of what actually high energy physics needs in terms of computing resources and capacity. And definitely this also complicates the situation a bit. If you think about the possible scale of challenges in some scientific endeavors, high energy very wide. You can think of high luminosity LHC, for example, with an increase in a factor of 60 or so, which has been already mitigated by constant activity by, of course, very focused groups, but still not at the point to make sure that phase 2 will be just smooth. We have at the same time SKA, for example, LSST, and Virgo LIGO for multi-messenger astronomy too. The goal in these endeavors is really to collect of the order of tens up to hundreds of petabytes per year. Virgo LIGO perhaps focus a bit less on data volume, but definitely they have challenging requirements in terms of processing velocity. And by the way, it's not only the scale given by the number of events that we collect, but also in the way we actually reconstruct and analyze these events. For example, we designed and built detectors that are very high granularity in many cases, and high energy physics as a community potentially will pay the price if they did not fold the computing costs in this design since the very early phase. So if you focus a bit more on the disk and at the bottom with the CPUs, despite these might not be the most updated plots, you get a feeling of the scale. In the very next few years, we are definitely a few factors away with respect to what is achievable by just the technology improvements itself. So which one? So machine learning definitely can be the solution to this massive problem. It can be definitely the part of the solution, and this is what I would like to address. To what extent? Let's see. I will definitely highlight some application areas of machine learning in high energy physics, but it's very difficult to focus everything in 30 minutes or so. And so definitely apologies to the many applications that I will not be able to cite. So first of all, why machine learning? Well, the challenging goal definitely fits. We have challenging physics objectives, tough computational requirements and environments to deal with, and definitely we need to perform predictions, as in machine learning is used to be said, which are sort of estimates in HAP jargon. To perform data-driven modeling, you need a lot of data. So big data in the real definition of a variety of V's. So volume for sure, but also velocity, veracity, etc. can well define these. Plenty of data are available, data being taken, but also plenty of simulated data, which is the fuel for the training phase of machine learning models. Definitely our community is much able to access high performance infrastructure. And if machine learning models can go on these infrastructure and work at scale, they can reach unprecedented performances, definitely. There is also a growing synergy with non-high energy physics world, which means that we are more and more able to formulate machine learning problems in a way that computer scientists and machine learning practitioners can actually help understand and help us on these. At the same time, there is a strong synergy more than years ago in terms of the tools and frameworks in machine learning that we can use. So we are not a confined, isolated community in that sense. We are less and less isolated, which is also a richness factor. So how can I discuss machine learning in app with a focus on machine learning? I could try to go through the possible algorithms, but probably this would explode in just a couple of slides. I can think of classifying different types of algorithm and tell where they are used the most and for which kind of results and studies. But then when I need to go into neural network, I will start talking about feed-forward neural network, maybe deep versions of these, then recurrent neural network, long short-term memory ones, GRU, gate recurrent unit, perhaps autoencoders as a family. So yeah, the generative version, variational autoencoders, but also denoising and sparse autoencoders. Then other possible models will come up down to deep convolution neural network and generative adversarial network. It's a bit complicated to give an overview, starting about the kind of models that can be used for energy physics. Then there is a different approach, perhaps. So why don't we focus on the high energy physics activities by themselves? And definitely this could be somehow more productive. Machine learning can be used in many areas. One, for example, is data acquisition and triggering. It's very important for background and trigger rate reduction to have, for example, to design specific trigger path for specific signals. It can help to do anomaly detection, data taken, up to do some unsupervised approaches towards new physics mining and things like this. Trigger in particular, and that's for whole experiment, it's very interesting in terms of application of machine learning because it's a driver of high performance machine learning application in high energy physics. So the design of the triggering processes that will be the next generations are sort of the key enablers of the real-time reconstruction, which in turn is the key enabler of real-time analysis ultimately. One of the challenges here is that, of course, there is a strong trade-off to be made between the algorithm complexity and the performance you want to achieve with the constraints you have. In this case, of course, there are very strict low latency time constraints, for example. Other possible activities, of course, are many. I can talk about machine learning in event generations. I'm not covering these in the slides, but in this case, I'm covering simulation and event reconstruction, for example. The simulation is a key area of work for machine learning. Simulation itself, so produce simulated events, is extremely computing intensive. Okay, and so it can directly impact the physics reach of experiments at the end. So you go through full simulation or you try to do fast simulation at least. And there is also machine learning enabled fast simulation, for example, because machine learning can help reduce such kind of load coming from event simulation. On the other side, event reconstruction too is challenging. So the both at the online level and at the offline level, the reconstruction can be replaced, at least in part, with surrogate models that are sort of approximate, so they can be faster, or by just brand new algorithms that can potentially yield unprecedented performances. This focus mostly, for example, on calorimeter or particle flows, etc. Well, there are other areas too, so the picture will not be complete anyway. Machine learning can also be used for operations because the data are not only collisions data. There are plenty of non-collisions metadata that have been collected, very rich in information, but very hard such information to be extracted from these, but they could provide interesting insight. This could help, for example, to increase the efficiency and reduce the manpower burden in many activities related to operations, from dealing with the data to actually computing operation at sites and over distributed infrastructure. You can automatize selected tasks, create a reactive system that are intelligent and can sort of be self-adaptive ultimately. And in general, you can expedite the entire chain from data collection down to the final analysis and to the publication. There is another aspect in which physicists actually could contribute in machine learning. And if you allow me, the adagio here is ask not what machine learning can do for yourself as a head physicist, but ask what, as a physicist, as a scientist in general, you can do for machine learning. There is plenty of work that science and especially physics could do in terms of modeling, also to build a solid theory behind what is actually the empirical success that machine learning exploits, shows in many endeavors. Okay, so this would be really difficult to go through. So I will try to a third approach somehow. So try to give you a feeling of the evolution of the machine learning adoption in high energy physics, because this gives us sort of how the community as a set of people with scientific curiosity moved towards this kind of technology, how the things have changed already, are still changing, and potentially give some insight about as of whether this will stop or continue and towards which direction. So let me start with a traditional, let's say, machine learning adoption in HEP, which was what happened until a few years ago, where the scenario was basically mostly focused on feature engineering. So you have basically physicists design high-level features to be used as input to traditional machine learning algorithms. So shallow one, no deep learning, no. For particle properties, energy resolution. Machine learning is used to improve the determination of the property of particles basically everywhere. Take calorimeters, for example. The energy deposited in calorimeters is recorded by so many sensors, which need to be clustered to reconstruct the particle energy that was there originally. So boosted decision trees are used by many experiments. In this case, I'm quoting CMS, to learn this correction using the information that you get from all the sensors. And you get a sizable improvement in the resolution, as you can see for the plot, on the plot. Also in particle identification. In this case, I'm quoting Wlcg, who used neural networks of the order of 30-ish features from all the experiment subsystems. Each of these networks was trained to identify a specific particle type, and basically they achieved a factor of 3 less misidentification in this approach, with the estimates now indicating that more advanced algorithm can actually reduce this background by another 50%. Then, of course, the discovery of the discovery of the boson itself. I'm quoting years for CMS, the deep photon analysis. Boosted decision trees here were used both to improve the resolution, but also to select and categorize the events, and allows to increase the sensitivity by roughly the same as collecting 50% more data. So in a nutshell, you can think of it as we were not supposed to discover the Higgs boson as early as 2012. In principle, given how the machine was progressing, we were expected to get a discovery, if Higgs exists, of course, by the end of 2015 or middle of 2016. That was the estimate. So the reason why we learn. And then you need to study the property of the Higgs boson. Take, for example, this from Atlas, analysis of tau leptons at Wlcg, quite complex. They decay before detection, so you lose all the subsequently produced neutrino. You have plenty of backgrounds from Z decays, etc. In this case, a BDT-based approach in various kinematic regions with a dozen of weakly discriminating features allowed basically to improve the sensitivity by roughly 40% with respect to a non-machine learning approach. And then you can continue with high precision tests of the standard model, even beyond the Higgs itself. CMS and LHCb were the first to find evidence of a very rare decay that happens basically once every 300 billions of PP collisions. And again, boosted decision trees were used a lot to obtain basically results that if you compare with just LHCb alone without machine learning, as a single experiment, it would have required the experiment to collect 4 times more data than it actually did to get to this scientific result. So this is basically what happened at the tradition until a few years ago, but something is changing recently. And the direction is going towards more advanced, more sophisticated machine learning techniques. And there is a change of pace in some sense, because we use neural networks, but the idea is that we use the full high-dimensional feature space to train deep neural networks. So we sort of skip the feature engineering step and we go really low level. We use all the features that we have and full neural networks with different architectures, of course, depending on the specific use cases. And this is extremely interesting because in doing this, we are sort of matching exactly the same research and progresses that happen in other fields out of HEP, like computer vision or natural language processing. And this makes an interesting synergy among the fields, by the way. So let's see some examples. For jet flavor identification, deep learning was used. The deep neural network here are nice because we have a large volume of simulated events that can be used for training. So we can easily fight over fitting and be better at generalization. Of course, the high level representation of jets are tough, but we can feed the deep neural network with large volumes of low level features. And this is why they are indeed powerful. And so let's exploit that power. CMS, quoted in this case, has been going through a review of different algorithms to identify heavy flavors, so the NC quarks generated jets in PP collisions at 13 TeV. The work went into moving from the original combined secondary vertex taggers that were used in LHC Run 1 towards a neural network version of these, which is the deep CSV algorithm, that gave already 15% improvement in relative efficiency with respect to other likelihood-based methods like jet probabilities, etc. And further work actually allowed to develop deep jet that can use full list of candidates in particle flow, secondary vertices, and actually has performance improvements and extend also to gluon jets, etc. So this is one area of application, for example. And another interesting approach is definitely, and this connects a bit also to computer vision, is to use convolutional neural networks. As we know, the CNN are loosely inspired by the structure of the visual cortex, and they are capable of identifying objects on images. They are based on strategies to decrease basically their sensitivity to the absolute positions of elements in an image. So this translation invariant feature learning characteristics basically allows this to be used very efficiently, like in self-driving cars and applications like this. If you use deep CNNs, you can extract very complicated features out of images. So this is interesting for us, even if in the industry sector, this is of course used for computer vision tasks like semantic segmentation of images. In high energy physics, this is interesting because it can be exploited in 3D images in detectors, event classification, etc. This makes this technique particularly suited, for example, for high energy physics neutrino experiments, but also in some simplified settings, at least in collider experiments, they are really promising and they are already giving some interesting results. As an example, let's take the NOVA experiment. The goal is to study neutrinos through precision measurements of their oscillations. The data collection strategy is interesting. In NOVA, they have a detector. The particle that are charged emits light when transverse it. And one single event in NOVA consists of 2 images, one taken from the top and one taken from the side. And they develop a novel machine learning based algorithm that uses 2 parallel neural networks, which are inspired by the Google NEC architecture, so inception node and things like this. In this case, the CNN is able to extract feature from both views simultaneously and combine them to categorize neutrino interaction in the active volume of the detector. And this yielded an improvement of 40% in the efficiency of the selecting, for example, electron neutrinos with no loss observed in purity. This is very interesting in searching for appearance of electron neutrino, but also for new type of particles, as we will see, called called the sterile neutrino. So in a nutshell, you can see here the experiments and the schematic view in 3D of the novel particle detector with the view from the top and from the side, and also a snapshot of the actual architecture inspired from GoogleNet of the neural network that they used in the experiment. Another expanding on the experience of MiniBoon, this large liquid argon time projector chamber is used to measure a lot of low energy neutrino cross-section and investigate astroparticle physics at large. The liquid argon detector is massive, and of course it's aimed at detecting neutrons sent from the booster neutrino beamline at Fermilab. One single event in microboon in terms of data collection strategy here correspond to an image that is 33 megapixel of resolution, and that might contain a signal of interaction of neutrinos, and you would like to disentangle these from background tracks coming from cosmic rays, and the size may be very, very wide, can be from few centimeters to meters, for example. They'll develop a new CNN-based method to detect neutrino interaction that exploit the sensitive information, the spatially sensitive information you have from the intermediate convolutional layers you have in the architecture of CNN to predict sort of a bounding box that contain the interesting region where the secondary particles are that are producing an interesting neutrino interaction. And actually, if you accelerate through GPUs the training and execution, the inference of these networks, they see a much better performance than any previous conventional algorithm used in neutrino experiments. So this is a generic technique somehow that can be used also everywhere you can move your problem into something that looks like a real-time image classification and object detection kind of task. In microboon, let me give you just an example of a neutrino selection and isolation from the output of the CNN. What you see here is the yellow box. The yellow box basically is a simulated neutrino interaction that is overlaid on a cosmic ray background image taken using the real detector. Important is to note that the CMS does not get any input this yellow box. Okay, so it doesn't see it. The CNF received the event display and is capable instead of drawing the red box. So to successfully localize the most interesting region there where the neutrino interaction happened, and does this with very high confidence. So this is to give you a feeling of how interesting this can be, this technology can be for neutrino experiments. Well, to those who claim that HEP is doing things differently and should be treated differently, these kind of images, especially from microboon, always make me think, because they use bounding boxes, they make me think of other application of convolutional neural network. And I really ask myself if we are so different as we think we are with respect to industry applications of this kind of technology. And I see basically no reason why we should not try, as we actually are doing, to cooperate as much as possible with machine learning experts in computer vision that are completely outside from the energy physics domain. Okay, so deep neural network are really a sort of appearing as a general tactics that can be used for larger time projection chambers, calorimeters, things like this. Every time you can represent the data as a 2 or 3 dimensional images, the problem can actually be easily or relatively easily cast as a computer vision task. And there is a perfect technology for that. It can even be a 4D, by the way, including timing information. And I will get to that in a second. So the reason why deep learning techniques based on deep neural network are indeed useful is because of this. They become really technologies that are good candidates every time you need to identify particles and extract some parameters in many experiments whose data can be treated visually in a sense. By the way, the architectures interesting in this deep learning are far not limited by CNN. You can easily do something different, like recurrent neural networks, for example. And I will give an example like along these lines in the following slides, this one. So recurrent neural networks are interesting because they are successful in many domains in processing sequences of data. So the concept is that they are based on recurrent neurons that have connections that point backwards. So in a way, they are able to, on one side, to treat variable length input, and at the same time to process time series by actually looking not at what happens at every single point in time, but actually accumulating and using all the information that you get across a sequence. This is basically the kind of technology that is used in Google for the translation services, for example. So in industry, time series is the application, which means audio, video, all NLP, all natural language processing, have a lot of application of these and similar architecture. In energy physics, we can indeed exploit these to build classifiers that are capable to process complex signal and inputs that can be of variable length. And tracks and particle in jets indeed have a time dependence, if you think of it, and also a sequence of these comparable with the sequence of words that you have in a sentence. You need to understand the full sentence by the word all together, exactly like you would like to understand the full event by the different particles, tracks, and jets as a whole, right? So these are used, for example, in big quarks identification. The beauty quarks are quite important at LHC in general. They are frequently produced in Higgs and top decays, predicted in SUSY decays and other theories, of course, beyond the standard model. They radiate energy into jets before forming bound state, and then basically after picoseconds with a flight range of the order of less than a centimeter, then decay into particles that are commonly produced. To identify these jets from high energy big quarks needs to find a displaced vertex, typically containing dozens of particles, so the number of potentially discriminating features may vary on a per jet basis. Methods like RNNs can be used to get the best out of low-level particle features within a jet. So you order the jet particles into indeed a sequence, you do some ranking, for example, by incompatibility with the being originated from the PP collision point. You feed a set of features for each of these particles to the neural network, and then you do the training to discriminate between big quark jets and other kind of jets. Various experiments are exploring this. Atlas did, and saw a misidentification rate reduced by 4 times with respect to non-machine learning algorithms, with additional reduction when the RNN itself is used as an input feature in the subsequent training of another model like a BDT or another neural network. CMS has basically much similar approaches. There are promising results. The neural network structure is slightly more sophisticated, but they are used in a more simplified setting. So you see, there is exploration by more than one experiment, and they seem to be really promising. There are other architecture, of course, that worth mentioning. First of all, the autoencoders. The autoencoders are feed-forward neural network, but the approach here is not supervised, is completely unsupervised. They tend to transform the input to the output by compressing the input, though, in a lower dimensional code, the so-called latent space representation, which is a sort of a compression, but it's not data agnostic, actually it's data specific, and can reconstruct the output from that squeezed input in a way, okay? There is, of course, a variational version of autoencoders, which is completely different. They are not discriminative models, but generative models. And they don't learn a function representing the data, but they learn the parameters of a probability distribution that represent the data, which is even more interesting because it learns to model the data. So you can sample from the distribution and generate new input data samples. So that's why it's a generative model. So the autoencoders in industry are used a lot for dimensionality reduction as denoising and things like this. And variational autoencoders in app in particular could really be used to isolate new physics as a sort of outlier of things we know. And there is something that we know very much on which we can train variational autoencoders, which is called the standard model. And this is basically the idea. For new physics mining at LHC, there is work in progress in thinking if variational autoencoders can be used by being trained on known physics processes, basically this standard model, so to build thresholds to isolate a physics event that were not seen, observed before. They're not compatible with the standard kind of events, and they just appear as outliers in the distribution. In this case, it's interesting because the way you train this stuff doesn't depend on any new physics signature you can think of. So you are completely free in the assumptions about the new physics modeling. And by the way, the way you do LHC searches in this case might be well complementary with respect to traditional methods, which are typically based on hypothesis testing that is model dependent, okay? The outcome could be a catalog of anomalous events that can be further scrutinized by experts, of course. You can look for recurrent event topologies in the catalog that may inspire focus searches and model building by theory colleagues, for example. Or you can even think of plugging this technique at the level of the trigger of the experiment, so to avoid discarding some potentially interesting events before they are thrown away with no way to come back. Okay, so this is indeed a promising approach to extend the physics reach of the Large Hadron Collider. Then, talking about the generative models, there are also the generative adversarial network, which are designed as a two neural network game where one basically fights against the other. One is a generator and maps noise to images and tries to fake the results in a way that the discriminator network gets cheated by that and cannot really disentangle the true and the fake. The other indeed has the task being getting information from both original samples, so both the real images and the fake images done by the generator, as the task to disentangle. Okay, so the best generator would be the one that is able to maximally confuse the adversary. This is used a lot in the industry in the industry sector to do image editing, generate data, and things like this. High energy physics, of course, has a wild need to generate stuff. And definitely for the simulation, it can be really interesting. It can simulate the detector response and may stand as a promising alternative to traditional simulation solutions, for example. And the simulations we know that are heavy. So the physics-based full simulation is really heavy for HEP, and Gen V even as the state of the art, if you want, but it's really computationally demanding. The idea of using fast simulation went indeed towards that direction, trying to remove some of that burden. But there are some promising alternatives based on machine learning for fast simulation. And really, if you use some high fidelity, fast generative models, that's an option, okay? It's still preliminary. We don't reach the required accuracy. There are inherent shortcomings related to the methods. It's very tough to train neural network like these with respect to others and things like this. But the first evidence seems to show that there is something to gain. There are orders of magnitude increase in speed over the existing, not full, but the fast simulation techniques. And definitely this is potentially a benefit for plenty of experiments out there. An example of simulations done with GANs is the Calo GAN, which is a new fast sim technique. It simulates the three-dimensional HEP showers in electronic calorimeter in multi-layer with GAN indeed. It generates the reconstructed Calo images using the random noise, basically skipping the entirety of the GEANT and RECO steps, the traditional ones, and make it 10 times faster than GEANT. Of course, the accuracy is not at the same level, but actually this is a very promising direction to go to. Okay,
Daniele,
so
we have about 3 more minutes. Sure,
I'm closing out with 2 slides. Perfectly in time, thanks. So what about the future? Well, it's very difficult to elaborate here, of course. I'm pretty sure that we will use some enhancement of currently successful neural network architecture. Quantum machine learning is at the door. This could be an option. Neuromorphic computing is another one. They are not mutually exclusive. So there are many interesting things that might happen in the future. My personal opinion is that the community has always been able to contribute to the technology process and actually profits of the recent advancement in technology in the infrastructure that we use both in R&D and in production. But there are mistakes that, of course, as a community we can do. And probably if we avoid at least a couple of these, we have a chance to go smooth. I'm not saying this is enough, but definitely these are mistakes we should not be doing. I think HEP should continue to embrace contamination with other disciplines and of collaboration that are growing. I think this should be underlined. And second, there should be a more concrete support to young high energy physics guys that are basically building the software and computing systems of the future, and they are growing their expertise in this sector. And this should be done concretely in terms of career recognition, because it's very easy that these very young and valid people tend to go out of the sector into the industry, and we lose basically the expertise, while it's exactly what we probably need as a community in the next future. So concluding, I think machine learning is ubiquitous in HEP. I try to give you a feeling at least of how the evolution is going across various areas. It's definitely different in terms of the chosen techniques and the adoption levels across various experiments, but also the techniques themselves changed a bit over the years. So we are embracing different techniques nowadays with respect to those that we used a few years ago, okay? There is among energy physics and researchers from the non-HEP world, so computer scientists and machine learning experts themselves. We need to be able to engage these people on our problem. And so to do so, we need to be open to the communities and also in using tools and frameworks and invest a lot in education of people that can be learning this stuff and be still attracted to the HEP goals and objectives. So if energy physics will be able to drive this process, I think that machine learning in our sector can play a crucial role towards meeting all the future challenges that we have in terms of data-intensive science at the energy and the intensity frontier. So I thank you very much for the attention, and I'm open to get questions and comments. Thanks.
Thank you very much, Daniele. So I'm the only one clapping here, but you can see all the other 50 people, which I now have not joined clapping, of course. Anybody, if you have questions, either put them in chat or raise your hand. I'm trying to see you raising your hand. Meanwhile, I have one question, Daniele. You mentioned the recognition for the young scientists. I think one of the issues is we're always asking them for high publication counts. But isn't software, I think you hinted at that, software also a valuable contribution?
I think this is a bit changing over the last few years. This was indeed a problem, and in part, I think still is today. So it's much more complicated to get something published if you work on a topic for many years, and if you work on software and computing, than it is if you do data analysis or detector development and similar. The thing is changing a bit. There are new papers. Is sort of raising the interest, I think, of all of us on this. And there is a chance now to do, let's say, less conference talk and less proceedings and a bit more paper journal in journals that have an impact factor that is growing. There is the Computing and Software for Big Science journal. There are specific machine learning journals. There are indeed occasions for young researchers to publish and to see that published in to see their work published in a peer-reviewed journal with the impact factor that is relatively growing and getting high. So I think this is the direction to go. So work and publish, and also considering the selection process in many countries. Of course, this is very different across countries and difficult to treat as a single problem, but also we should do some pressure as much as we can in our different endeavors to make sure that people working in enabling technologies for scientific discovery like software and computing should be treated exactly as people building detector and things like this, things like that. I think that software and computing basically are a sort of a sub-detector nowadays of all next generation detectors, and the more they are, the better it's for the future of HEP, I think.
Sounds good. Daniele, you mentioned change. Now, Tiziana has also posed a question in the chat. How will machine learning transform or change the compute infrastructure of Wlcg?
Well, definitely machine learning is eager to get data at full speed and eager to do linear algebra as quickly as possible. This means very fast performance ingestion rates of data and input, and whatever allows to do parallelizations at the level of the linear algebra that is needed to train the model and compute the weights of neural networks and all that. So definitely being able to access heterogeneous computing resources on a large-scale infrastructure would help basically both on the hardware setup and on the software setup to make sure that the most computationally intensive part of the workflows will be intelligently able to match the perfect resource available. So I'm looking forward for a future in which we can decide exactly which specific part of every specific job goes to which specific processing unit that might find available on a site. This is, of course, a large goal and work in progress, but I think it's definitely a sort of a synergy across many things that happened over the last few years that are continuing to evolve in the next future. And I think there's hope to do something interesting in the next 5 to 10 years on those.
Mm-hmm. Simon is also raising a point from the past. He says in the 1980s and 90s, many condensed metaphysicists have been working on the development of neural network theory. We should also get contaminated by other branches of physics too. And I think you mentioned not only physics, but many more fields that play into the realm here.
Yeah, I think different disciplines, of course, at different moved at different pace. One thing to remember is definitely that many of the things that we discussed in the second half of the talk, let's say, so about deep learning, are really at the edge of technology somehow over the last 10 years or so, due to the rise of big data, to the availability of technology and processing units that allows basically to train such complicated models that are very computing eager of computing resources, and at the same time also the ability not to need to buy complicated stuff and put these on premise somewhere, but actually to sort of access this kind of resources through cloud interfaces. So the mixture of these is basically common across a variety of disciplines, and now it's becoming more and more fertile as a ground to discuss with other communities, because the needs to share the infrastructure, to share the experience, and to use common infrastructure, and if possible, so similar tools to do data-intensive science is becoming more and more similar with respect to how it was up to 20 years ago or so. So I think indeed it's a very fertile time to get into this game.
Thank you, Daniele. I think this was a wonderful start into the day with your lovely talk. I'm just asking Kento if there has been any other questions posed.
I'm sorry, but I'm not
see any other question, and the time is up.
Okay, thanks. I'm not seeing the chat, so I cannot intercept any myself.
That's okay.
Sorry.
We're taking care of that, Daniele.
Okay,
I think if you just release the screen, I would hand over to Tiziana to start the screen sharing.